we are going to use the Chatelier's principle to explain what happens to a reaction that is in a state of equilibrium. What does a state of equilibrium mean? I'm going to deliberately swap the reagents around so that you can get used to this way of writing it as well. It is possible for us to start with ammonia. So if you only have ammonia in the reaction mixture, what will the initial rate of decomposition composition of ammonia be, where the nitrogen and the hydrogen gets back into ammonia? What will that reverse reaction rate be? Zero. So your forward reaction always starts at a high rate. Your reverse reaction always starts with a zero rate. Okay. If the reaction, like we wrote it down yesterday, the forward reaction was exothermic, what is this forward reaction? Endothermic. Okay, so delta H is going to be positive. This reaction takes place in the presence of an iron oxide catalyst. In industry, this takes place with an iron oxide Fe2O3 catalyst, and the temperature range is 450 degrees to 550 degrees. That's the temperature range that will give the best yield. Oh my, of ammonia. Okay. So the reaction is in equilibrium, is the situation. So what does that mean? Say it. You can be wrong, I'll fix you up. Say it. It's not a disgrace to be wrong. Now, what does it mean? The system is at equilibrium. What do you mean? The products and the reactants are the same?
There's the same amount of products formed as well as reactants.
How can you say that? Wait. I'm just listening to her. Why are you saying it that the products and the reactants are the same amounts? Because they even react in the ratio 2:3:1. How can you say that they're the same amount? We can't say that. But the amounts won't change. Whatever the amounts are, they won't change. And this I haven't said yesterday. When a system is in equilibrium, the amount of ammonia won't change. The amount of hydrogen won't change. The amount of nitrogen won't change. I haven't said this yesterday. When a system is in equilibrium, there will be no observable changes in the reagents. Okay. But for every molecule of ammonia that decomposes into hydrogen and nitrogen, there would be a hydrogen and a nitrogen forming ammonia. What does that mean? Mfihlakalo, that is where I stopped you to say it. What does it mean that the system is at equilibrium?
The rate of the forward reaction is equal to the rate of the reverse reaction.
Yes.
You said when in equilibrium, there will be no observed change in the reagents.
Yes. Because the amount of ammonia won't change.
Man, by amount, are you talking about the mass, the concentration?
Mass, mole, concentration. Concentration is technically the amount per unit volume. technically the mass per molar mass. So mass, volume, moles, concentration, all those are ways of measuring the amount. Okay, ready to roll?
Yes.
Okay. This is the change we are going to bring. So the changes I'm going to discuss. Let's take first a change in concentration. Now, which one's concentration do you want to change? Let's make it a spontaneous one. Do you want to change ammonia's concentration, hydrogen's concentration, or nitrogen's concentration? Ammonia's concentration. What do you want to change it to? Do you want to increase it, or do you want to decrease it?
Increase.
Okay, so let's increase the ammonia's concentration there, and let's draw a line, and let's say we decrease the concentration in the second instance. So decrease. Now concentration, the square bracket around the formula of a compound or an element means concentration. So here we're going to decrease the concentration. When you write it down to answer a question, please don't use the up and down arrows. It's just me trying to save space. Good. It's a system in equilibrium. We're pumping more ammonia into the system. What is the reaction going to do?
Going to increase the rate of our reaction.
If they pump ammonia into the reaction, what will happen to
It won't be in equilibrium anymore, and it will fight to stay in equilibrium.
So how is the system going to react to reinstate equilibrium?
Now we'll break up the ammonia so that the hydrogen and nitrogen are equal, so it goes back into equilibrium.
So the opposing the disturbance, opposing the increase, can... I will listen to everybody, but I can't listen to everybody at once. So you put more ammonia in, the reaction that will decrease that amount of ammonia will be favored. Which is which reaction? But the reverse reaction makes more ammonia. So the forward reaction shows that the ammonia is decomposed into hydrogen and nitrogen.
It depends on what's
Okay.
written down, how you look at it.
Yes, it does depend on how the reaction is written down.
Because we thought that
that was the forward reaction.
the one that we did
The
yesterday
forward
was the
reaction
opposite
is
of this.
always from left to right. Okay. So an increase in the concentration of ammonia will favor the reaction, the forward reaction. Which will
Make more nitrogen and
tend to decrease the concentration of ammonia. Will all the added ammonia be used up?
no.
No. Because before all the added ammonia is used up, a new equilibrium will be reached. So this, favoring the forward reaction, shifts the equilibrium to the right. the concentration of the hydrogen will increase and the concentration of the nitrogen will increase.
So ma'am, once you change the concentration of something, it will go back to equilibrium, but a different equilibrium.
It's a different equilibrium, yes. It's a different equilibrium. Now you can explain what will happen when you decrease the concentration of ammonia. When you remove ammonia from the reaction mixture, what are you going to write down?
The decrease in
You'll favor the reverse reaction,
which will tend to increase the NH3, the concentration of NH3.
Yes. So the equilibrium will shift to the
the
left and the concentration of the hydrogen and nitrogen will decrease. Okay, write it down. If you start off with ammonia, then there will be no hydrogen and no nitrogen in the container. Then the rate graph will look like this. This is a rate graph. The forward reaction will start high, and as the ammonia's concentration decreases, the rate of the reaction will decrease. In the same time, as hydrogen and nitrogen is formed, you start off with naught. As it is formed, the more hydrogen and nitrogen you have in the reaction chamber, the higher the rate of composition of ammonia will be. So your forward reaction always slows down. Your reverse reaction always speeds up. Okay? Until the new equilibrium is reached. When the new equilibrium is reached, the rate of the forward reaction and the rate of the reverse reaction is equal. Okay. Now, I want to look at the rate graph when we introduce more ammonia into the system.
What's that one? Ma'am?
that one.
Ma'am, could we go back to this line?
Adding ammonia will speed up the forward reaction.
So do we see that?
So look now, because this is new. So the forward reaction rate shoots up
If you add ammonia.
if you add ammonia.
Oh, okay.
Okay. Okay.
I'm going
So
to write there, add ammonia.
I'm going to. But now, so that reaction is favored. Sorry, so which reaction is favored? No, yes, you're right. The favored reaction is the forward reaction. Now, the sudden increase in ammonia shoots up the rate of reaction. But it needs to re-establish a new equilibrium. So the new equilibrium the forward reaction will slow down again. What's going to happen to the reverse reaction now? Eyeball, you have more hydrogen and more nitrogen forming over time. So it will also, it won't shoot up. So if you add reagents to the system, you're going to speed up the reaction. The collision theory says an increase in concentration will lead to more effective collisions per unit time because you've got more molecules present. But the reverse reaction will increase in rate slowly or slower. That forward reaction increase rate will be, it will shoot up because you're pumping in more ammonia. Yes.
So that increase in the concentration, so that shoot up with the disturbance that is caused, right?
Yes.
And then its tendency to go back down is
to reach a new
so,
equilibrium.
yes, but here, ma'am, I'm trying to correlate it with the words that's here. That would be when it says will favor the forward reaction, which will tend to decrease. Would that be that thing where it tends to decrease?
Tend to decrease the concentration of ammonia.
Yes. Would that be that?
Yeah.
So when it shoots up and comes back down, that's what it tends to decrease.
Yeah.
Okay.
So because it's shifting to the right, that's why the reverse reactions rate is going up and the forward reactions rate is going down because it's going away from shifting to the right.
Yeah.
It's clocking me now.
So when it shoots up, right, it's gonna wanna decrease, but at the same time it's decreasing, the
What's T?
hydrogen and the nitrogen are increasing to try and meet up at the same.
To try and reach a new equilibrium.
Right.
At point T0, remember the x-axis is the time axis. At point T0, ammonia was added. That means the rate of the forward reaction will increase. Suddenly. I'm trying to verbalize what I've put on the screen there. To re-establish the new equilibrium, the rate of the forward reaction must decrease while the rate of the reverse reaction will increase.
Ma'am, what's that 2 for?
The rate of the forward reaction will increase suddenly to re-establish the new equilibrium.
T0 is the point at which ammonia was added.
Yeah. The rate of the forward reaction must decrease because the ammonia is busy being used up again, while the rate of the reverse reaction will increase. Because the concentration of hydrogen and the concentration of nitrogen will increase. So a forward reaction, a change is induced, the forward reaction will speed up suddenly by adding ammonia. The reverse reaction will speed up gradually in order to reach a new equilibrium at a higher rate.
So then, ma'am, if you added even more ammonia, then it would go up again.
Yeah, but they won't ask that. Okay. Now, for you to grow, draw the graph of the rate of reaction when you take ammonia out of the reaction mixture. Try, even if you try in pencil, you can try from the equilibrium state. So we can try from here. We can try it from the place where the forward reaction and the reverse reaction is in equilibrium. So I'm trying to expose you to the different ways that the questions can come your way. So here we are looking at the reaction when it's in equilibrium. I'm not looking at from the start when initially the ammonia was put into the container.
So that's points as TO basically.
This is TO now.
But now
This is now at point TO.
But now we're decreasing.
You remove ammonia. So think about it. If you take ammonia out, what is going to happen to the rate of the forward reaction?
Decrease.
So draw it in, even if you use a pencil, try. What's going to happen to the rate of the reverse reaction? So if you remove ammonia, you drop the forward reaction suddenly, and then slowly new equilibrium must be established. So as more ammonia is formed, the rate of the forward reaction will speed up. As less hydrogen and nitrogen is present in the reaction, the reverse reaction slows down. Okay, I wasn't sure. You may go, I'm just going to finish this video. So favoring the reverse reaction, decreases the concentration of hydrogen and nitrogen. So the reverse reaction slows down until new equilibrium is established at a lower rate. What are you saying? Oh, you're talking something else.